Okay, so in the first video, there was apparently some technical difficulties, and the last part got cut off. So I'm going to just restart this, or I'm going to go over the last part one more time. So we left off on propagation of action potential. Propagation allows for the action potential to be transmitted from the origin of the stimulus down to the entire length of the axon towards the terminals. The sodium influx through the voltage gates in one membrane area is going to cause the local currents that cause the opening of sodium voltage gates in the adjacent membrane areas. So that's gonna lead to depolarization of that area, okay? Because the sodium goes in, that depolarizes that area where the sodium channels are located. It depolarizes that area and then it moves to the adjacent area. So it depolarizes the adjacent area as well. And that's going to allow for those sodium channels to open and more sodium to come in. So once the action potential is initiated, it's going to be self-propagating. In non-myelinated axons, each successive segment of the membrane depolarizes, and then it's going to repolarize. And propagation in myelinated axon is going to be different because in myelinated axons, the sodium channels are going to be closer to the action potential origin, and they're going to be inactivated. So those channels cannot be, if they're inactivated, they cannot generate a new action potential. Okay, so the action potential in myelinated axons, it only moves forward. Here you can see the propagation of an action potential and how it's read by an electrode that's placed on an axon. So to begin with, the axon is more negative on the inside, it's more positive on the outside, so it is polarized. And so at this point, the electrode is just reading the inside, and so it's reading that it's more negative. So this is at 0 milliseconds, so it reads it at a negative 70 millivolts. As the action potential reaches the electrode, then this area here becomes depolarized, so it becomes less negative or a little more positive. And so now the electrode reads it at a plus 30 millivolts. And then as the action potential travels farther away from the electrode, the area is going to become more negative, and so it's going to read it uh, down to negative 90 millivolts because this area is still hyperpolarized because the action potential just passed through here. The central nervous system is going to tell the difference between a weak stimulus and a strong stimulus by the frequency of the impulses, because the frequency, the frequency is the number of impulses received per second. So higher frequencies are going to mean a stronger stimulus. So if we look at the stimulus voltage down here, so we can see that for this first one, the threshold was not reached, so no action potentials were generated. On the second one, the threshold was reached, so even if the stimulus just barely got it over the threshold, that was enough to generate action potentials. So all of these are action potentials, so there's 4 in here. On the third one, the stimulus was a lot stronger than this middle one, and so it generated action potentials, and it also generated more action potentials. So you can see the difference between a weak stimulus and a strong stimulus. So when there is an action potential, there's 2 types of refractory periods that occur. There's the absolute refractory period, which is it happens right at the peak of the action potential. And then there's the relative refractory period that occurs after. During the action potential, all the sodium channels were opened, and so that allowed for sodium to come in and depolarize the membrane. But then afterwards, those channels become inactive. So once they become inactive, no new action potentials can be generated at this point. As we move past the absolute refractory period into the relative refractory period, some of those sodium channels are still inactive, but some of them are not inactive. So in this space, or at this point, there can be a new action potential that's generated if there's a strong enough stimulus. And that stimulus can occur at any point here. So if there's a strong enough stimulus here, it'll generate action potential. Strong enough stimulus down here, it'll generate an action potential. So it just depends on when it receives that strong stimulus to bring it to threshold. Okay, so this is where I left off on the last video. And so the next slide continues on part 2.